So we finished kind of the conversation last time with the discussion of various molecular shapes that can be predicted using the approach that is called VSEPR. Okay? So, and we figured that you have to consider, when you think about the shape of the molecule, you have to consider the arrangement of the, I'm going to change the color, sorry. The arrangement of the electron pairs, that the free electron pairs, the lone pairs as we call them, and the arrangement of the bonds. Okay? So, for instance, in the molecule of CO2, we have lone pairs at oxygen atoms, and then we have bonding pairs between the carbon and the oxygen. So in order to maximize the angles between the bonding pairs and the lone pairs, the only arrangement that will work is the arrangement where the molecule has a linear shape. Remember we talked about it. So if we move on to another molecule, a molecule of formaldehyde, okay? Now in this case we need to look at the arrangement of the bonding pairs and the lone pairs again. So in the molecule of formaldehyde, you have two bonding pairs between the hydrogens and the carbon. Does that make sense? Do you see that? Then you have another two bonding pairs between the oxygen and the carbon. Does that make sense? And then we have two lone pairs at the atom of oxygen. So how can you maximize it? Technically, what you can do, you can draw the molecule like this, right? You can draw it. Nothing prevents you from doing that. But in this case, what's going to be the angle between the bonding pair that forms between oxygen and carbon and the bonding pair between carbon and hydrogen? You know what I'm talking? What's going to be this angle here? 90. What's going to be this angle? 180. Now, you see, you have two pairs that are too close and two pairs that are considerably far. From energy standpoint, it will be more preferable to kind of equalize these angles. So, how can you make them equal? You make all these angles 120 degrees. Does that make sense? Mm-hmm. You can ask, what about these two lone pairs? These two lone pairs will not influence these angles because they will be basically shaping like this, like rabbit ears. They will stick out like this. Okay. Now, another example is the molecule of sulfur dioxide. Now, in order to properly draw this molecule, let's do the number of valence electrons. Okay. So, sulfur, let me erase it for a second. We've got sulfur, we've got oxygen, and we've got another oxygen. Does that make sense? How many valence electrons total two oxygens and one sulfur have? How many valence electrons total these three atoms have? How many valence electrons on oxygen? Huh? 18. So 6, 6, and 6. Does that make sense? 18. So how many electrons have been used for each bonding pair so far? 2 and 2. Right? How many electrons are left? We have 18. We used 4. How many are left? 14. So we distribute these 14 electrons trying to make an octet. So let's try to do it one way. So we're going to place electrons here. Okay. How many electrons I have used so far? 12 plus the 4 at the bonding. That was a good question. 16. I have 2 left. I place this 2 at the sulfur. Now, oxygen, does it have an octet? Oxygen does. What about sulfur? Sulfur doesn't have an octet. Do you see that? Well, I mean that it doesn't have 8 electrons. It has 2, 2, and 2. It has only 6. So what do we need to do to make an octet at the sulfur? Huh? Say again? Can't hear you.
Add 2 more.
We can't add 2 more. Well, we add 2 more, but we don't add. What do? We share. We take 2 electrons that belong strictly to oxygen and move them as the double bond. Does that make sense? So first, we figured out that this molecule is going to have this arrangement. Right? Does that make sense? Now, will it be linear? It won't be, because sulfur has a lone pair. This lone pair is essentially electrons sticking out. Does that make sense? So these electrons, this lone pair, repels each of these bonds. Does that make sense? So the ideal shape will be not linear because of that lone pair, but it will be bent because you have one bonding pair, another couple of bonding pairs, and the lone pair sticking out here. Does that make sense? We never draw the lone pairs, but they determine the shape of the molecule. Does it make sense? Now, this we already saw. That's methane. We talked about it, how to distribute 4 bonding pairs in the space so they will be as far from each other as possible. And we distribute them in the way so that hydrogens in the molecule of methane are located in the angles of tetrahedron. Does that make sense? I try to... So basically, if you think about this, this is how it's going to look. Look at my fingers. So these are 3 bonds that look downward, and there is one bond sticking upward. Like this. Does that make sense? So that's the molecule of methane. And the angle between these bonds will be 109 degrees. Similarly, we can figure out the structure of the ammonia gas. So the formula is NH3. We can draw the arrangement like this. Okay? But this is not going to work, obviously, because the angle between these 2 bonds will be each 90 degrees. This angle will be 180, and on top of that, there is a lone pair. Can you see the lone pair? Right here. So how can we arrange basically 3 bonds and a lone pair sticking from the nitrogen atom? Think about the lone pair as the bond that doesn't bind anything. Does that make sense? Like just a stick sticking out of the atom. You understand what I'm trying to say? So in this case, we do basically the same arrangement. We do tetrahedral arrangement. The only thing that is different compared to the molecule of methane is that in methane we have 4th hydrogen, and in the molecule of ammonia we do not have that 4th hydrogen. The lone pair sticks out here. Does that make sense? The lone pair sticks out here. So we still have a pyramid where nitrogen is at the top of the pyramid and hydrogens are at the bottom. Does that make sense so far? Now, water is a molecule with, again, with 4 electron groups. And you can see that we have oxygen, which forms bonds with 2 hydrogens. And oxygen has 2 lone pairs. Does that make sense? You see this rabbit ears? In order to arrange this lone pairs in the best way possible, think about this. We still have to make some kind of a tetrahedron. But since we are not drawing the lone pairs, all we can see is the oxygen, 2 hydrogens, and there is an angle between them. Angle that is approximately equivalent to 109 degrees. That makes sense? Oxygen is here. Hydrogen and hydrogen. That's the lone pair. That's the lone pair. Does that make sense? So what you essentially see is this bent molecule. So this table summarizes the examples that we used. And to make it kind of straightforward for you, I'm not going to ask you of any other examples than the ones that we talked about in the lecture, okay? But for these ones, you have to know the shapes of these molecules. Am I clear? Good. So how do you predict the shape in general? So first, you need to draw the electron dot formula. That's your step 1. Okay? Next, you need to arrange the electrons so that the repulsion between the lone pairs and the bonding pairs will be minimal. Does that make sense? So basically you treat your lone pairs just like bonding pairs. But in the end, you kind of remove the lone pairs from the view and you use only the atoms that are connected to the central atom and you determine the shape. So for instance, here in the molecule of carbon tetrachloride, you have 4 bonds around carbon. Does that make sense? How can you arrange them in the best way possible? You have to put them in the shape of tetrahedron. Does that make sense? Like I showed you this way, and the 4th is sticking upwards. In this manner, the repulsion between the bonds will be minimal because the angles are going to be optimal. So that's the shape of the molecule. Does it make sense so far? Now, why do we play with such apparently deeply theoretical idea as the shape of the molecule? What kind of practical information can we get by knowing the shape of the molecule? Turns out, if we know the electronegativity of individual atoms and the shape of the molecule, we can predict whether a particular molecule be polar or nonpolar. Are you following? Here's how we do it. Obviously, molecules like oxygen or hydrogen, they are nonpolar. Does that make sense? Because atoms are equal, they have equal electronegativity, they pull on electrons with equal force, so there is no change in electron distribution. Does it make sense? Let me go back for a second. Where is electronegativity? Yeah, so here, there is no change in electron distribution. These compounds are not compounds. These chemicals, these molecules are by definition nonpolar. H2, O2, Cl2, they're all nonpolar. Do I make sense here? Now, what if molecule does consist, in this case, of 2 or 3 atoms with different electronegativity, like the molecule of CO2. So here's the question. So, which atom in this molecule will pull electrons towards itself? Oxygen. So what's going to be the charge on oxygen? Partially negative. And charge on carbon? Partially positive. But if you will figure out the shape of this molecule, and we just did, CO2 is the linear molecule. Does that make sense? Now, I will have to use the analogy. Imagine that oxygens are quite literally start pulling on carbon. They're going to pull on it with an equal force. So these pulling effects of oxygen, they will cancel each other. Does that make sense? So despite the fact that each bond is polar, the molecule as a whole is nonpolar. Do you understand what I just said? Now I'm giving you a second just to think. So despite the fact that each bond is polar, the whole molecule is not. Because the pulling forces, we call them dipoles, the pulling forces that oxygens exert on carbon, they cancel each other. Does that make sense to you? Let's look at another molecule shown here. A molecule of carbon tetrachloride. So, what has higher electronegativity? Chlorine atom or carbon atom? Chlorine. So chlorine will pull the electron density towards itself. Does that make sense? So each of these bonds will be polar. Is that clear? Now imagine you have to imagine the carbon in the center, and the carbon is being pulled by basically 4 ropes to the angles of the pyramid. Does that make sense? All the pulling forces, all the electron attraction that is exerted by all the chlorine atoms, all these attraction forces will cancel each other. So despite the fact, that each bond in carbon tetrachloride is polar, the whole molecule is not, because dipoles are canceling out each other. Does that make sense? Generally speaking, if the polar bonds are arranged in the symmetrical fashion, dipoles will cancel each other out. Does that make sense? Do you understand what I just said? So for instance, I can give you another example, pretty similar to what we talked about. A molecule of carbon disulfide looks like this. It's linear. What's more electronegative, carbon or sulfur? Sulfur. So sulfurs are going to be pulling electron density towards themselves, forming 2 dipoles. What's going to happen? Is that molecule symmetrical? Yes. So dipoles will cancel each other out. Good? Now, when molecule becomes polar, and dipoles do not cancel each other, like in the molecule of hydrochloric acid, okay? Hydrogen chloride, HCl, okay? That makes sense? So chlorine will pull electron density towards itself, and there will be slightly negative charge formed in chlorine and slightly positive charge formed in hydrogen. So we've got a typical dipole. It's pretty easy when we talk about molecules that consist of 2 atoms. But what about molecules that consist of 3, which is molecule of water? We just talked about the fact that water molecule is shaped as an angle. Does that make sense? So there are pulling forces. Oxygen will pull electron density towards itself from one hydrogen and from another hydrogen. But let me ask you this, these pulling forces, will they cancel each other out? They won't. And the reason for it is that the molecule is shaped at an angle. Does that make sense? So it's like, think of it this way. If somebody will grab my hands and will start, 2 people will start pulling me to the sides, and they're going to pull me with equal force, am I going to go anywhere? No. But if I will stick my hands like this and they will start pulling me, am I going to be moving? Yes. So that's the same idea. You think of it as somebody is pulling on the molecule. Does that make sense? So, molecule of water will be polar. The molecule of ammonia gas will be polar. Because think about this. All these pulling forces, they will, I shouldn't say propel, they will not cancel each other out. All those dipoles, all those polar bonds, the dipoles on each polar bond will not cancel each other out. Does that make sense to you? So, how you determine if the molecule is polar or not? First, you need to determine whether or not the bonds are polar. Next, you need to determine what is the shape of the molecule and whether or not these polar bonds, these dipoles, can cancel each other. So, for instance, molecule of oxygen difluoride. Okay, in this molecule, the bonds between oxygen and fluorine are at an angle. Which element has the higher electronegativity? Fluorine. So each bond will be a dipole. Does that make sense to you? Will these dipoles cancel each other out? They will not, because they are at an angle. Does that make sense? The whole molecule will be polar. Now I'm going to throw a really curveball at you. So I will try to draw it. Apologize for my drawing skills. So that's the sulfur hexafluoride. Okay? Now let me explain how it looks. You see central sulfur and 4 fluorines. There's 4 fluorines. Can you see them? They all are on the same surface. Does that make sense? Sulfur is in the center, 4 fluorines at the angles of a square. Does that make sense? 2 more are sticking out like this. 1 here, 1 there. Does that make sense? Do you understand what I'm saying? So bond goes up, bond goes down, 4 bonds here. Each bond has the same length. Are these bonds polar? Yes. Do they cancel each other? Yes. So that's perfectly symmetrical molecule, and despite of the great polarity of each bond, it will be a non-polar compound. Does that make sense? Are we good? Why do we pay so much attention to the polarity of the molecules? We can predict the polarity of different parts of molecules like amino acids, integral component of a protein, or nucleotides, integral component of DNA. We can, at least hypothetically, predict how these molecules will interact with each other and how they will determine the shape of the protein or DNA. Does that make sense? So we can basically identify several types of interaction that can exist between various molecules. We've already talked about ionic interactions. Does that make sense? So those are interactions between charged particles. We clear? Now, polar covalent molecules, okay, can exhibit dipole-dipole interactions and hydrogen bonds. For instance, look at the molecule of hydrogen chloride here. Chlorine atom is more electronegative than hydrogen, so it will accumulate slightly negative charge. Does that make sense? Hydrogen atom of another hydrogen chloride molecule will accumulate partial positive charge. So that partial positive charge and that partial negative charge will form a bond. It's not a chemical bond. You have to appreciate that. Does that make sense? It's not a chemical bond. What's the definition of a chemical bond, by the way? When does it form? Huh? There are 2 different elements here. Huh?
Is it to create a new
No, you can't create a new element. You can create a new compound, but, well, when does chemical bond form? When atoms exchange what? Exchange or share electrons. When this bond is formed, there is no electron exchange or sharing. Does that make sense? It's the bond that is formed purely because of the electrostatic interaction between slightly negative and slightly positive charges. Are we clear? So this is not a chemical bond technically. It's a bond between two molecules that will determine the properties of a compound itself, blah, blah, blah. Does that make sense? So hydrogen bonds are formed specifically between partially positive, hydrogen atoms, okay, and the lone pair on fluoride, oxygen, or nitrogen. Does that make sense? So what does that mean? Let me show you using the example of water. So water molecule has two lone, oxygen in the water molecule has two lone pairs. That makes sense? And it has slightly negative charge. If you take another water molecule, hydrogens will have slightly positive charge. Can you see that? I draw it. So this hydrogen and this oxygen establish hydrogen bond. All right? You see that? Got it? So hydrogen bonds are absolutely essential to know if you want to understand the structure of the protein and the structure of the DNA. Those are the bonds that hold DNA strands together and determine the shape of the protein molecules. So far, we good? Can non-polar... Now, think about this. It's pretty simple idea, simple exercise before we actually go to this. Water, which is a polar molecule at the room temperature, what physical state does it have? Liquid. And it's liquid because there are very, very strong hydrogen bonds between individual water molecules. Is that clear? Because water molecules are attracted to each other very strongly. Second question. Say nonpolar molecule of carbon tetrachloride, CCl4. Okay, they're nonpolar, so they don't form hydrogen bonds. Does that make sense? Interestingly enough, this compound is also liquid at the room temperature. Now, what does that mean? It means that those molecules of carbon tetrachloride, actually interact with each other. Does that make sense? They interact with each other. They form some kind of non-chemical bonds between the molecules that hold them together at the room temperature, preventing them from evaporating, basically. We clear? These bonds are called dispersion forces. So in dispersion forces, the molecules form what is called a temporary dipole. So basically, molecules just bump into each other, and due to that bumping, they form a dipole, which leads to the formation of a dispersion force bond. Right here in the center, I've very conveniently colored it out. Okay? So here you see the bond formed by dispersion forces. These forces are weak, okay? Very weak. But there are very many of them usually. So that explains how they may lead to, molecules forming liquids at the room temperature. Does it make sense? So dispersion forces, weak attractions between nonpolar molecules. Now, generally speaking, these forces, dispersion forces, hydrogen bonds, or ionic interactions, are responsible for the certain melting points of the substances. In general, ionic compounds have the highest melting points because interactions between individual ions are extremely strong. Polar covalent molecules have lower melting points, but still pretty high, so you can expect them to be liquid at the room temperature, or if they're solid, they're going to melt much more readily. Does that make sense? And compounds that form dispersion forces have the lowest melting points. Does that make sense? However, we can say, okay, carbon tetrachloride is liquid at the room temperature. It's nonpolar molecule. Does that make sense? Hydrogen sulfide, is it polar molecule or not? Hydrogen sulfide that I just drew. It's angled. It's polar, but it's a gas at the room temperature. So you can't really compare two given molecules. You just have to remember that, generally speaking, ionic compounds will have highest melting points. Polar covalent will have kind of in the middle. And nonpolar covalent will be at the bottom of melting point. Okay, those are some examples. For instance, melting points for these ionic compounds are extremely high, about 1000 degrees Celsius. Melting points for compounds with the hydrogen bonds are kind of in the middle. Okay, that's dipole-dipole interaction, which are weaker than hydrogen bonding. And finally, dispersion forces. In order to get a liquid chlorine, you need to cool it down to negative 100 degrees Celsius, which is pretty low. Does that make sense? So in order to help you out with that, this table compares various types of bonds and attractive forces. So in ionic bond, there's an exchange of electrons. In covalent bonds, there's sharing, yes. Hydrogen bonds, dipole-dipole interactions, and dispersion forces are not chemical bonds. We can call them physical bonds that are formed either via electrostatic interactions between two dipoles, okay, hydrogen bonds being the strongest, or temporary interactions between temporary dipoles in case of dispersion forces. Those are weakest. We're good? Questions? Did you see the study guide? 6 p.m. tomorrow. You're going to be surprised.
Oh, thank God.
Don't thank God. Thank me and my kids, because they're writing it. They quite literally writing this answer thing.
Wow.
But one more thing. There are few questions on the study guide. You should know how to blah, blah, blah. Like, blah, blah, blah means that some statement there, okay? So, like, you should know how to write a formula based on the name, how to write a name based on the formula. Does that make sense? and on that kind of line of thinking. The entire homework is about that. I selected the problems from the book so you can practice, okay? And if you will go to the end of the chapter, you can find the answers, okay? Now, here's the thing. We are not in the 5th grade. If you decide, oh, screw that, I'm just going to go back to the back of the chapter and just write all the answers and that's it, you might guess. It's not cheating. Sure, go ahead. You will not practice, and it will not really not help you on the exam, but, you know, that was your choice. So we're all adults. So I encourage you to do those problems and then compare your answers with the answers at the end and see, okay, I got this right, I got this wrong. And if you have, like, issues with that, if you know that you have issues with that, address them today.
We can always.
Oh, the periodic table, yeah. You can use periodic table all the time. Okay, does that make sense? For naming, writing, it's totally fine with me. Okay, and any questions on what I want you to know? No, we good?